Good morning again, everyone, and welcome to the final topic in Unit 4. We're going to be moving the trig identities to our next unit because we have a weird schedule where we see each other a lot and then we don't see each other at all. So I definitely want to cap off tomorrow with some kind of evaluation of your learning for this week, and we don't want to stuff more in there than we can fit. The last topic that's new for grade 11 in trigonometry is adding the third dimension. These types of problems will often create situations where you have to solve one triangle and then create a second triangle and solve that triangle. And just multi-step problems where we're still working in two dimensions at one time, but in these cases, having a well-labeled diagram and building your capacity to visualize now not only in two dimensions but in three dimensions, that's going to be critical to success. The other new topics that we have, the idea of angles in standard position, reciprocal trigonometric identities, and special triangles, these will be very useful when we start looking at trigonometric functions in the next unit. And I've been just dying to share with you trigonometric functions because, as I mentioned before, this is my favorite course, and I think trigonometric functions are one of my favorite topics in mathematics. So we're getting there. But today we're looking at trigonometry in 3D, and our steps to solve, this is the main one. Do not skip, do not underestimate, do not short yourself on this labeled diagram, okay? You want to create diagrams. You might draw one in 3D and then multiple 2D triangles as well. Just like when we were looking at Julia and her kite, and we were thinking the kite starts at 60 degrees and then goes down to 45 degrees. That creates two triangles. They're still in two dimensions because they're all on the same plane. So if I was looking at it from the side, I would see the kite go down, and I would see that creates two different triangles. But because the triangles are superimposed upon one another, our diagram gets pretty messy if we keep it all in one place. So draw two separate triangles and understand that they all come from Julia's hand there. They all start in the same spot. Then, just like we do in two dimensions, you're going to choose your methods, SOHCAHTOA, sine law, or cosine law, to solve these types of problems, and then solve the problem. Finally, you're going to want to interpret your findings. You want to write a final statement that explains the numbers you found. This is important for several reasons. One, we're not doing math in a vacuum to show that we have the ability to get our calculator to cooperate. It's not our purpose. Our purpose is to use mathematics to understand the world and to use mathematics to change the world. One of the ways people use mathematics to change the world is by influencing other people's behavior. So if you are in the search and rescue helicopter and you are seeing these triangles as you look down and you see the target, the person that you're trying to find, and you look down another triangle and you see the search party, you're trying to influence that search party's behavior to go exactly the direction they need to go to save the person that they're trying to save. If you tell them just a soup of numbers, they can't use that to influence their behavior in an efficient way. You must interpret your answer for your audience. And that goes for all types of questions. We have an exponential function and it shows the value of money over time. If I say the answer is 5 million, that doesn't mean the same thing as you will have $5 million after following this investment strategy for the next 40 years. And $5 million looks like this type of house and this type of car. So please sign on this dotted line so I can make my commission. You want to get that signature at the end of the day, you need to interpret that number for your audience and make it relevant to them. So that's my spiel there. If you're like, oh, this is math class and not English class, Mr. Jennings, sorry, we're all humans and we all communicate, so it's still critical. Okay, so another thing to think about is we have cardinal directions. We've all agreed that north is north, south is south, and east and west lie this way. We don't consider the curvature of the earth when we're looking at these types of things. It's not like, I think it's Bill Gates' favorite riddle or someone's favorite riddle. I go, Here's a riddle for you. I walk 1 kilometer south, I walk 1 kilometer west, and then I walk 1 kilometer north. So I've walked in it, and I'm back to where I started. So where is that true? Where am I? I walk 1 kilometer south, 1 kilometer west, and then 1 kilometer north, and I'm back where I started. Ha! And I have to change the direction of the treadmill? Yeah. No, it's not true. It's a great answer. No, that's not what I'm thinking. Is that a hand up? No?
Wait, you walk north, south,
I walked 1 kilometer south, 1 kilometer west, 1 kilometer north. You think I'm 1 kilometer west of my starting position? Yeah. That's true in most places of the world, but there's one place where it's not true. Yeah. Yeah, the North Pole. If you walk south from the North Pole and then walk west and then walk 1 kilometer north again, you're back at the North Pole. It creates a kind of circular triangle around those places because it does not make a right angle. East and west, north and south do not make right angles when you're that far north. Down here, the curvature of the Earth, yeah, it's a factor, but we're basically thinking that it's a right angle, and that's how we do the math. Okay, so we are simplifying. Okay, the next thing is to think about bearing. And so the way we talk about bearing is going to have an effect on interpreting some of these questions. Now, we have two examples that we're going to go through here. And the first example is a kind of cautionary tale. Just because something looks like it's happening in 3 dimensions does not mean you need 3 dimensions to solve it. So let's read this first question. We have an inaccessible cliff, so draw the cliff. Okay, and we want to find where is, and we're looking for the height of this cliff. So I'm going to draw my cliff. I'm going to draw it over here. All right. We can't get to the top, so I can't just drop a measurement down. And then from point A, so that's going to be point somewhere over here. This is point A. The angle of elevation to the top of the cliff, 38 degrees. And then from a second point, 68.5 meters from A, the line of sight between point A and the base of the cliff is 42 degrees. So here, this point B, it must be closer. Here's our point B, okay? And then we're looking up. And we're looking up now at 42 degrees. And the distance here between B and A is given as 68.5 degrees, 68.5 meters. So I only need 2 dimensions to show this, this problem here. So this will be a review for us. If I have a 38 degree angle here, a 42 degree angle here, and a base, I know angle, angle, side. And what I want to know is the height here of this triangle, the height here of the cliff. What rules can I use to solve this type of question? Yeah.
38, is it on the left angle or the right angle?
Yeah, I'm going to redraw my diagram. This is 38 degrees here. Okay. This is 42 degrees in here, and I have another triangle. So first, identify all your triangles, and that's going to help you choose your strategy. I have a triangle here, and I would like to know the height here. If I can determine this side length, I could determine this triangle. I could solve it. But right now I know no side lengths for this triangle. I don't know anything about it. Okay. The only thing I know is it has a 42 degree angle. Does that give me more information about this triangle that I'm looking at here? This one that I will highlight in purple. So here's my other triangle. And they share a common side. I know this is 38 degrees. I know this side. So I know one angle and one side. What else can I find out about that triangle? Dave? Yeah, I can find all the angles here. So this one here, what will this angle B be interior to this triangle? 138. Great. So this is 138 degrees. And then this triangle up here, let's label it C. So angle BCA is what? 4 degrees. Yeah, because if this was 140 and that was 40, it would be 180 right there. We shaved 2% there and 2 degrees there. So that's together 4 degrees. So that looks good. So now I have one triangle that I can solve. I could also tell you this angle up here, but I'm not really going to need it for this problem. Now I'm going to draw two triangles based on my diagram here, because my diagram is admittedly quite janky. So I'm going to take my first triangle, triangle ABC, and then we can label this point D, and that would be triangle BCD. But triangle ABC looks like this. It has a side there, it has a side here, and then a side there. And we knew this was 38, this was 138, and this was 4 degrees. And this side is known at 68.5. What rule do I need to, what do I want to find here? What's my desired known? That's an unknown right now. Oh, well, this triangle doesn't have a hypotenuse because it's not a right angle triangle. Oh, but the hypotenuse of BCD? Yeah, I want to know this side, because this is the side that's shared by both triangles. And if I knew that, then I could calculate the height of the cliff. So what I'm going to use, what rule do I need to use to find this side length? Call it x. Label it on both diagrams here, x. Label the common side. Sine law, great. I have an opposite pair of angle and side. This side is 68.5 and this angle is 4. And I know that this x is sitting across from this angle 38. So I know all the things that I need to know to solve that. So I'm going to set up sine law. My desired unknown is a distance. So I'm going to put my distances on top when I set up my sine law. This is going to look like this. 68.5 divided by sine 4, which is going to be a very small value, is equal to my unknown x divided by sine 38, which is going to be a small number, but not super small. It's going to be a little bit bigger than a half. So to solve this one, I'm going to multiply both sides by sine 38. So I'm going to have this expression here, sine 38 degrees multiplied by 68.5. Divided by sine 4 is equal to x. That gives me something I can punch on my calculator. I'll race you.
Yeah.
Who has it? 604.57. So 605. We'll keep it to a meter. That will be plenty enough. Oh, wait. We should keep the same number of digits as the problem. So you said 604.58? 57, so 604.6. 604.6 meters equals x. Great. Is that the answer we were looking for?
No.
No. Is it an important step in the getting of that answer? Yes. So I'm going to circle it. I'm going to come back to that number. So I like to be able to find it easily when I'm looking at my solution here. Just move me out of the way. Now we're going to take a look at our triangle and redraw another diagram here. I'm going to draw a second triangle. And that's going to give us the thing that we want to solve. So here's triangle CBD. Oh, I didn't notice that I did that. Here's triangle BCD. And it's got a 42-degree angle. It's got a side length now of 604.6. And I want to know the height of the cliff. Call it H. So now, notice that my diagrams... What did I do there? Oh, that's 02. Okay, let's clean that up. It's 42 degrees. So now, what will I use to solve this triangle and to solve for H? Yeah, this is just a SOHCAHTOA problem. So take your known angle, 42 degrees, and which one do I use? So, sine, cosine, or tangent? Sine. How did you know, Dave? Yeah, you got the hypotenuse, you need the opposite. And sine relates opposite to hypotenuse. So that's how you know. Yeah. So it's good. And just like I was saying before, you want to be able to use math to influence other people and influence their behavior. And one of the ways that you're going to be able to do that is by explaining your methods very clearly. So when Dave's able to say, well, I can see that the ratio of sine 42 relates my known to my unknown. That's how I can solve for my unknown. That's going to be nice and clear for your audience when you're telling them. So that when I multiply by 604.6 is going to give me 604.6 multiplied by sine 42. Just use your inverse operations to solve for h. Punch this on your calculator, and that will give you the answer, the height of the cliff. 404.6? This is why it's an inaccessible cliff. It's very tall. 404.6 meters equals the h. Am I done? I need a therefore statement. I need to interpret this for my audience. Therefore, the height of the cliff is 404.6 meters. Great. And there we go. What else to say? Now, I said this is important because you want to use math to communicate and to help other people adjust their behavior so that you can get your desired goals completed as a team. Another thing this does is it reinforces for you that you understand the number that you just found. And it's a great way to check your answer. If for some reason you punch this in on your calculator and you forgot to push multiply here, and it just gave you the sine of 42, which is, somewhere around, what is it, 0.6 or something like that. And then you said the cliff is 0.6 meters tall. Well, that's not a cliff. That's like a big speed bump. So you would know, okay, that can't be the right answer. I better go back to my math and check it. Okay. All right. So now let's take a look at example number 2. Now we have a 50-meter tall bridge and 2 boats are at the docks. Oh, we better take a break. So let's go on break, and when we come back, we'll finish the lesson. Welcome back from break, everyone. So we had one question like, where did we get this angle here? This 138. And my diagram is so ugly because I really appreciate everyone's patience with me and my new technology and how slowly I'm learning it, but I'm really not very artistic yet. Maybe I can work on that and improve. But if I draw this more beautifully, here's the cliff. Here's my initial one with 38 degrees. And then this one is looking up at 42 degrees there. And I have this as 42. If this is 42 degrees, this all the way down to there is 180. So this angle here is 180 minus 42. That's how we came up with this 138. That's how we came up with that 138 degrees in here. Okay. Yeah. Thickness. Let's go much thinner. And that will be better. Okay. So that's how we get our angles there. That's how we solve for these unknown angles, is using our basic geometry that a straight line is 180 degrees. So now let's take a look at this question. First, we read it and work to understand the question. From the top of a 50-meter bridge. So you'll notice I've already drawn my bridge, and it's 50 meters tall. So I'm going to do my triangles I'm going to try to do them in 2 colors here, red and blue. And I'm going to start this one. This line is going to be part of both triangles, and you'll see that in a second. This line comes down, and it's 50 meters going straight down. This is 50 meters high, this bridge. 2 boats are seen at the docks, okay? So one boat is seen at south 50 degrees west. The way you read that is you have your primary direction here south. We're looking south. So I've arranged this with north looking up and south is coming towards me. Cut it in through the page and out of the page is my north south. Is kind of how I'm looking at it. And that's pretty intuitive. We usually think of north as being up and south as being down. And that's totally arbitrary. There's no universal truth that makes it so that this has to be north and that has to be south. You can imagine the globe upside down. And we're down under and Australia is normal. Anyway, so here we are. We're looking south and then we want to go 50 degrees to the west. So the west would be that way. So if it helps, you can draw your N, S, E, W here. And that can help organize your thinking as well. And so we go south and then 50 degrees west. So this line going here towards this boat is making a 50-degree angle with south. That's 50 degrees. I really want to zoom in, but I want to read the whole question. And it has an angle of depression of 38 degrees. So that means I'm looking down at the boat, down 30 degrees. It also means the boat is looking up at me at 30 degrees. So that's where I'm going to choose to label this angle, is right in there. And I have no undo button when I'm in this program. No, I just want to grab you. There. Okay. And so I'm going to draw the rest of this triangle here. So this boat looks up at the bridge at 38 degrees. Okay. And it's off of this line that goes straight south by 50 degrees. This is pure south. Okay. Now my next boat, it is south 60 degrees east. So it's over this way. We're going to use purple for this triangle. And so it's out here. And notice this point down here doesn't look like a 90-degree angle, but that is a 90-degree angle there. Because it comes straight down, meets the ground, and then goes straight along the water. It only doesn't look like it's 90 degrees because I'm trying to represent 3 dimensions in 2-dimensional space. So this boat comes along here, and we look for it east, 60 degrees east of south. Okay, so that gives me this interior angle of the triangle here, 110 degrees, and this one is looking down at a 35 degree of depression. So it's where the boat is looking up at 35 degrees at us here. Now, it might not be immediately obvious why, if I'm looking down at the boat 35 degrees, why is the boat also looking up at 35 degrees? It's a variation of, if I have 2 parallel lines, I'll show you here. People remember this idea? If I have 2 parallel lines, so this is me looking out along the horizon. This line represents the water. If I'm looking down, if I look down here at 35 degrees, this angle will be what? 35 degrees. Yeah. And so these 2 angles will be the same. This angle x will be over here, this angle x. And that's a property of parallel lines being cut by a transverse. So the angle of elevation that this boat looks up at is also 35 degrees. Now this is a very beautiful problem in that we only have one known distance, the height of the bridge. And then we measure the angle that we're looking down at the boat and the bearing of the boat from us. And then we measure the angle we look down at this other boat and the bearing of that to that boat. And from that, we can create another triangle here. Let's use green, will be the most distinct color now. Now we'll create a third triangle, which is going to be here. this is our desired length. We want to know the distance between the two boats. How far apart are these two boats? Label it. Call that the desired distance. We'll call that D. Okay? We want to find D. In order to find D, we're going to need to know more about this triangle. We have 110 degrees there. That's all we know about it right now. So we want to think, what's our road to a solution look like here? What are we going to need to find out to find D? Write down what you know. I've just written down everything we know about this problem in this diagram. And then look at what you want to know, and then work backwards from that to find your road to the solution. Dave? Yeah, how far are both boats from the bridge? We're not caring about how far they are from the person. We want to know how far along the water are they. These sides here and here are common to this triangle. So let's label those sides. We can call this the first boat. We'll call that A, distance A, and this one distance B. Okay, and then if we have A and B in this angle, then we could use one of our trigonometric ratios to solve this triangle. What trigonometric ratio would we be using there? Sorry? Nope. We can't use sine law because we have a known angle here, unknown, unknown. We might know this side and that side, but we don't know this side. So we have a known angle and an unknown side. We can find this out. We can find that out. We can't find these angles out.
Are the bottom right angles?
So Cosine Law will do it. Yeah, so these are right angles here. These are right angles there and there.
But like at the bottom, the green line?
No, this doesn't necessarily make any right angles. This is 110 degrees here because I just add how far from west from 60 that went and how far east that went. That'd be 110. So these are right angle triangles. How can I solve these triangles? I want to solve for A and B. So if I want to solve for A and B, expand your diagram and create more triangles. So this is boat number 1. And that's going to have a triangle that looks like this. Oh, let me do this in the matching color. So that's going to make it just that much more beautiful. Beautiful. Okay, so here is the one triangle. This is the position of the boat. Let's label that A, boat A. So this is point A over here. All right. And then this over here is the bottom of the bridge. That's 50 meters. And this is a right angle. And then I label my 38 degrees. And I want to know this length A. Okay, that's my first thing to solve. So go ahead and find that for me. I'm not going to go step by step. I expect people to be able to do that now. If you can't do that yet, then you do want to hit me up for some questions and figure this out. This is point B. This is boat B. So I'm going to have another triangle that I need to solve, which is triangle B. It has the same side over there, 50 meters. But this angle here is 35 degrees. And this is side B. So I want to solve for A and solve for B. And then I can use those together with Cosine Law. If I know that and I know that and I know this angle, then I can use that to find D using Cosine Law. So notice that our method was first draw a diagram, write everything that you know down, and then figure out what it is that you want to know and decide your road to a solution from there. And then you'll work back the important things to solve. You don't need to know everything about all these triangles. You need to know the things that you need to know to get the desired information out of the problem. So, who has an expression that we can use to solve for A? Dave, you've been busy today. Someone, not Dave, not Siraj.
I actually have a question.
Okay, great.
You've labeled the triangles A and B, right?
Well, I labeled this boat A and this boat B, so that's point A and point B. You can imagine this point there is that point there.
You're also looking at the lines that are underneath as A and B, and it gets a little bit confusing because then you can think of the angles.
Oh, yeah. Yeah, because they're not associated angles, right?
Not opposite.
Yeah. Fair. I could be labeling these a little more elegantly. So long as I keep it straight in my mind, it's going to be okay. But yeah, these are not related triangles, like related side angles of these things. I just don't even think about that at all if I have a right angle. As soon as I have a right angle, I'm not thinking about related sides and related angles because it's just a SOHCAHTOA thing. Yeah. Oh, but once we go to Cosine Law, yeah, you're right. I could flip the names of the boats. Who can tell me how to solve these for little a and little b? How I can solve for this length and this length?
Matching side and angle.
Yeah, so I have right angle triangles here.
Oh. Yeah.
I could solve this angle. Do I need to?
No.
No? Does it cut down any steps if I do it? I have a right angle triangle. So when I have a right angle triangle, what do I do? Is the triangle right angled? Yes. Does it involve any angles? Yes. Use trigonometric ratios, sine, cos, and tan. Okay? These are just SOHCAHTOA problems. So how do I use SOHCAHTOA to find for these unknown sides? I know this angle, 38 degrees. I know this. What side is that? Is it the opposite or the adjacent? Adjacent. I have a known side. Is it the opposite, the adjacent, or the hypotenuse? Yeah. What trigonometric ratio relates opposite to adjacent? Tan. So write down what you know. I know that tan is the one I want to use. I know that tan 38 is something that my calculator can tell me what it is. I know that tan 38 is equal to opposite over adjacent. So write that down. 50 over A. Now you have some inverse operations to do to solve this. Multiply both sides by A, divide both sides by tan 38. Okay, you want to see that? Want me to write out my inverse operations? Yeah, okay. So I'm just going to need to zoom in because I'm going to need to use the space very effectively here, what the space I've given us to do this problem. Okay, so now I multiply both sides by A, and I divide both sides by tan 38. That's going to cancel this and this. Leave me 50 over tan 38 on this side. When I do A over tan 38 on this side, okay, then that's going to cancel this tan 38 on that side. Leave me A equals 50 over tan 38. That's something I can punch on my calculator. Let's write that out again. A equals 50 over tan 38. And now I'm still feeling like maybe I'm going a little quick with these inverse operations. So let me show you how you solve that. Tan 38 equals 50 over A. Oh, darn. My unknown is the denominator. That's annoying. So multiply both sides by your unknown. That brings it to the top. That's going to be one step to removing it from the bottom of a division problem. Then, oh no, now I have A times tan 38 on this side, and that's awkward. So now divide both sides by tan 38. Because there you're multiplying A times tan 38. You don't want to do that. You want to know just A equals. So divide both sides by tan 38. Yes, you can do both of these inverse operations at the same time by multiplying both sides by A over tan 38. Then we get this, and so what is it?
63.9970.
A equals 63.9770?
9970.
Okay, so that's 64. 64.0. And I think we were given this without a decimal place, so we'll just keep it to one decimal place. So that's 64. Okay, so let me erase that. So we have A is equal to 64. Notice that we're building up more information about our triangle, the one that we're eventually going to solve with Cosine Law over here. We now know this side. Might as well put the number on now, 64. This is 64 meters. All right, now let's find B. Is B going to be longer or shorter than A? Yeah. We're looking up at less of an angle. That means we have to be further away to look up to see the same point at the same height. So yeah, we're expecting an answer that's going to be maybe like 70, 75, somewhere in there. That sound like a good guess? Do it. Find me B. It's the exact same math. So what you're doing now to make use of your time and to not be super bored is to say, I am going to solve this problem myself. I'm going to write down tan 35 equals 50 over B. Then I'm going to solve that for B. Then I'm going to get an answer. Is my answer in that range? Is it a little bit bigger than 64? That would show me that my math is correct. Try it. I'm not going to write it out again. It's the same steps. So what is it? What's B? What are you guys getting? I know you have it.
71.4.
Great. So B is 71.4. So we're going to call it 71 because we're just keeping one decimal place here. So now I'm going to label that. This is 71 now. And now let's write out our other triangle. We're going to draw the last triangle that we need to solve for this problem. And it's the triangle ABD with bridge. Okay. Oh, I was going to do this in green. So here is the base of the bridge up here. Here is boat B and here's boat A. Okay. We know that this side was 64. This angle was 110. And this side was 71. And our unknown is D. And we have noticed this is known side, known angle, known side. I don't know these two angles. I have no pairs of opposite angles. I have no right angles. When I have no right angles, I can't use SOHCAHTOA. When I have no pair of side and opposite angles, I can't use sine law. So I'm down to cosine law, the most complicated law, the most difficult to use. Dave?
If you break this triangle up to right angle triangles, you can on the side you do have the 50 and 60 degree.
50 and 60?
So you can find the other.
Are these right angles over here?
No, so you can find angle A and angle B.
Do I know either of these angles?
No, I'm talking about the ones on top.
Up here? These ones?
Yeah, so you can find angle A.
This angle here?
Yeah, and angle B.
No, I can't.
You can?
No. No. Why do you think you can, Dave?
Oh, wait, never mind.
Because those are at 90 degrees.
Both are-
Yeah. One is an angle coming down this way. The other one is an angle going out that way. So they're not, because they're at 90 degrees to one another, they're not known. It's an angle this way. And it's some unknown angle. Also, these ones here are not necessarily 90 degrees because this is not level to, this is not an east-west line. So this is the situation that I have. These are all the knowns that I have, and that's it. So I have to use cosine law. So this is the way I set it up. D squared is equal to 64 squared plus 71 squared minus 2 times 64 times 71 times cosine of 110. Okay? And now it's probably a good idea that I write out my general rule, my general law, where I get that from, to help people out. This is a variation of, if I call this d squared, it's equal to a squared plus b squared minus 2ab cosine of d. Okay? We usually write this down with a c there, but we named this side d because it was the distance that we wanted to find. So this d is related to this cosine over here. It's related to the opposite cosine. As that cosine opens up, it influences that length. And we use this formula to find it. So this is just plug and chug on your calculator, but there's enough going on here that I would plug and chug it individually. I plug and chug the different pieces. So this to me is one piece, 64 squared plus 71 squared. That's easy to do on my calculator. 64 squared, where's my squared button? There it is. Plus 71 squared. Oops. Go back. I have no delete button. 9137. So I have 9137 here from these two, minus 2 times 64 times 71 times cos 10. So maybe I'll do this in one piece and then do cos 10 last. So let's do that. 64 times 71 times 2 equals 9088 times cosine 110. Okay, now I do that on my calculator. Multiply by cos 110 equals, now that's negative 3,108. So this, when I do minus a minus, that would be a plus. So I have 9137 plus 3108. And then I get the final answer. I'm just going to add this. I'm going to subtract 9137 to get the distance here. This is the distance squared is equal to 12,245. And now take the square root of that. And I get, it's beautiful, 101. 101 meters. Now, before we do a therefore statement, we should probably look at our initial diagram. We're 50 meters above the action. This boat's 64 meters away. This boat's 71 meters away. We have just found that D is 111 meters. Does that look reasonable? This is an angle 120. It's pretty wide. And these add up to a little bit more than this. So that's very reasonable that that would be the answer. And so then we can wrap this up and say, therefore, the boats are 111 meters apart. Ding, 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 ding. Done, done. Okay. So I hope this shows you the importance of at least keeping your diagrams straight and organizing them well so that you can get your numbers organized, look for the unknowns that you need to know, find those, and then use all of that together to find the answers to these types of problems. Any questions, certainly hit me up by email or bring me over now. We've got about 45 minutes where we can practice some practice problems. The practice problems up here, 1, 3, 6, 7, and 20 on page 265. There's also problems on the back of your handout. And then people can also start taking a look at the review, page 276, 1 to 12. Make sure that you're capable of answering those types of questions. Bye for now.